How we doing? Talk about the first two. This one I think I'll just put off. Yes.
If you find that the first integrals are just, do you need to do the second one, or will it just better to do this one?
Saying no, but I remember the case last year where they later combined.
Yeah. Oh, never mind. I got it. Because it's a two. I was thinking 1 over 2.
If they had logarithms, for example, I love those things, but if they have different limits, I don't think they could. So I guess you're on safe territory. I see what you're saying. Hey,
I just don't like having to write limits.
Oops. Yes, I have.
You're comparing it to 1 over 9.
Yeah. Okay, sorry. 414, did you get converge your diverge? Okay, let's see, 1 over 2, x equals 2 squared from 0 to a. Okay, so as far as this one goes, when you plug in A, it's something like 1 over negative 2 times A minus 2 squared plus 1 over 2, 0 minus 2 squared, yeah? I'll come to this one in a second. As A goes to 2, what does this difference go to? 0, and therefore 1 over 0 goes to negative infinity. So this approaches negative infinity plus something. If these were the same limit, they're possibly converging or combining, but because they're different limits, they can't be combined. So it's just going to diverge. Okay? One quick note or two on the homework I saw. First of all, on such a place where the discontinuity is inside, you should have 2 limits, and these should be different. A and B, not A and A. I had at least 10 people or so write A and A. They need to be different. They're different things approaching different numbers. First, second, I absolutely grade for this. I have people just saying approaching 2, not giving any thought to what side they're approaching from. That also is not okay to me. You should show what side they're approaching from. Is that understood? Okay. What approach did you use on 10? Yes, sir. Sure. It would, but 1 over 0, 1 over tiny goes to infinity, right? This is 1 divided by a billion, which is a billion, and 1 divided by a trillion, which is a trillion. Okay? Okay. Okay, what did you use on 10? Limit comparison test. It is a comparison test. What did you, let me communicate the minimum amount of work I would expect. What did you compare it to? 1 over n squared. If you show me this, then you don't have to show me this. I would be okay if you went straight to the reciprocal version, which is this. But I definitely need to see one of these two. This to me, to start there, is not okay. You're identifying what you're comparing to. You're already taking the reciprocal too much. Okay? I need to see one of those two. Is that clear?
Yes.
Okay, what is the limit? 1. So great. For the benefit of Michael, who was not here yesterday, what does that imply? That the two series, yeah, there's proportionality between the terms. Basically a 1-to-1 proportionality. The terms approach almost equivalent. And so they have to behave in the same way. So our first statement is to say, because that limit is between 0 and infinity, then they both converge or diverge. If it was 0, that would mean the top outpaced the other, and if it was infinity, sorry, I switched that around. But they didn't behave the same. So, both converge or both diverge. Now what do I say for my second part? 1 over n squared converges. You have to say that that converges in y. B series equal to greater than 1, so the given series converges also. Okay? Something along that line, those lines. I'll warn you again, if you just write versus 1 over n squared, or you just find the limit but don't write the statements, do me a favor, just skip it all together, because it's going to be minus 1 either way. Don't waste your time. All right? If you're going to do it well. And if you're not going to do it well, skip it. I'd rather you not develop that habit, please. So, 11 was pretty much the same deal, except this time it diverged. Okay, let's go to the lesson. I just love this lesson. So much fun. You'll love it. So, first of all, that's Swiss. That's not Euler, it's Euler. It's pronounced Euler. Euler's method. He's a great mathematician about the time of the Bernoullis, so it's really Leibniz and Newton are the forefront, early 1700s, late 1600s, and then the next generation starts to take this calculus ideas and go off in all these cool ways. This is one of those ideas. So, Euler's method is the idea that, say I had a differential equation like this, dy dx equals x plus y. How'd you integrate that? Separate the variables. Okay, separate the variables. Exactly. Good silence. Good silence. That is a non-separable differential equation. You cannot separate those variables. It can't be done. So the problem then is, how do you integrate it if it's non-separable? The answer is you don't. You can't integrate. Now the problem is, however, sometimes I know the derivative, and yet through the magic of calculus, you could say, I can't integrate this, but I could still find f at 4 or f at 3 or whatever you want. If you just gave me a point, I could just use the differential equation to find f at 8. Pretty magic. Here it goes. Check it out. By way of introduction and warm-up, estimate the square root of 27 using differentials. We need that to use Euler's method. So let's remember that. Root of 27 is equal to root of 25 plus some change in y. Is that true change in y? If I wrote a hard equal here? Yeah, that's plus true change in y. Now, I don't know true change in y, because if I did, then I wouldn't need to estimate. I would just do the actual change. But we estimate this with 5 plus dy. The idea being that the tangent line is a pretty doggone good estimate of the curve. In this picture, here, I remind you, this red segment, that's true change delta y. This green segment, that's estimated change dy. You follow? And for points close by, they're pretty close. You with me? For both of these, we stop at the same point. So delta x and dx, they're the same. I have control over how much I go over. That's not an issue. I can call those both. Am I recording? Oh, put that. Okay. I don't want to do that. Oh, phew, so close. Phew. Okay. Can't tell you how many times I've done it. So here we go. How do you find dy? The derivative at some good initial point times dx, and I can write dx or delta x there. Again, that's not an issue. What is the rate of change? What's the derivative? 1 over 2 root x. At what point will I find that slope? At 25. And what's delta x? 2 or negative 2? 2. Okay? The best way to remember that is not to say, what is it, x old minus x new. And that, just say, do you expect the answer to be more or less than 25? And we expect it to be 4. Right? All right. So, this is 5 plus 2 tensor, 5n, 1/5. Are we cool? All right then. The big idea of differentials is that dy is, y, my bad, sorry, y new, let's call it y of n plus 1. Well, we started at y of n. Y of n plus 1 is like starting at some y and using a derivative at the previous point, x n y n, times an amount of change in x. Sweet? Old y plus change in y gives me new y. Cool? All right then. Now let's lay that on top of a visual slope field. I'm going to do this a little bigger. Okay. Would you please draw a slope field for the differential equation 2x at all those points? Yes, I'm aware that that is 80 points. Go. All through. Stop line it and just do it. You'll see there's a pattern. It should take you 30 seconds.
Still not good. Okay. Something like that, yes? Why is there no variation in slope as we go vertically? Because the derivative depends on x, not y. All right, so there's variation. If you read a slope field, remember if there is variation horizontally, that means x matters. The derivative depends on x. If there's not variation vertically, then it doesn't depend on y. That's what's going on here. These other questions here, again, leading to a point. Say you sketch the particular solution through 0, 0. When I do that, I start at the point they give me, and I start to follow the slopes. Now, the first slope says go horizontal, but the minute I go horizontally, I get to one that says, all right, now go up 2 over 1, and then it says go up 4 over 1, and then it goes up 6 over 1. So I start to get something like that. Usually, instead of choppy segments, you draw it smooth. Okay? You follow? All right then. Now, say you were interested in f at, oh, wait a second. Oh, I skipped part C. find and graph the true particular solution, So we kind of followed our slopes and we got a sort of picture of the particular solution. Let's actually integrate and find the real particular solution. When we integrate a differential equation, we first separate the variables. At least for separable we do. And so y is x squared plus c, given the initial condition is 0, 0, then it's y equals x squared. So really it should end at 416, right? Okay, say you were interested in f at 4. What is f at 4? 16, all right? Stick with me, I have a point. If you use your slope field particular solution through 0 to estimate f at 4, okay, this is what I mean. When we started at 0, 0, I had you change slope the minute you got to a new one, right?
Yeah.
What if you had just said, all right, I'm going to start at 0 and estimate at 4, I guess in essence like just one single tangent. If I just kept that all the way to 4, then my estimate would be that f at 4 is roughly 0, okay? Now surely that's a really terrible estimate of the true f at 4, yeah? Why is that? How come a tangent line fails? Why does a tangent line differ from the true curve? I just said it for you. It's a curve. It's a curve. Because it curves, the tangent line will keep going at the same direction because it's always uses the same rate of change. And the curve curves. The curve curves. Why does a curve curve? Because it's a curve. I was looking for more. Because the slopes change. The slopes change. The slopes change. All right. This is a terrible estimate because the slopes change right after x equals 0. Now, we got a better estimate when we used our slope field because we used different slopes as we go from x equals 0 to x equals 4. Now, that really is the essence of Euler's method. You use slopes, but it's not a visual. It's really more of an analytical exercise. Here it goes. And I'm going to use a visual because it helps you truly understand, but eventually the graph will not be something we do. It's usually an analytical exercise. Check this out. Say I use the same differential equation, dy dx is 2x. The same initial condition starting at the origin. And this time, instead of trying to get from 0 straight to 4, I'm going to go 0 to 2, recalculate, and then go from 2 to 4. So, my initial point, my initial x is 0, my initial y is 0. 0, not x. I guess that's true. No. x1, the first x I want to go to is to 2. That's what they asked me to do, all right? So, y1. By differentials, y1 would be y old, start from where you were, then go the change at where you were. The where you were was 0, 0, times an amount of change in x, which is 2. I'm changing by 2 in going from x of 0 to x of 2, right? All right, well that is 0 plus, what is the rate of change at 0? 0 times 2, so my new y is 0. That seems like it's lame, but it's not. It's really cool. I went from 0, 0, and it said the slope is 0, so just go straight until you get to the new point, 2, 0. But that's okay, because now we're going to get a new slope. x 2, our next x, will go from 2 to 4, and y2 is y1, the previous y, plus a new rate of change at what point? 2, 0, yeah. The previous point where we left off, 2, 0, times a change in x of 2. y1, where we left off, y was 0. The new slope, what is it? Given that it's dy dx is 2x at 2, 0, 4. I would expect now to get a rate of change of, or a total y change, or new y of 8. Because I used a new slope, now I'm going to say by the time I get to 4, I would end at 1, 2, 3, 4, 5, 6, 7, 8. Yeah? Now, it did a decent job of approximating what we know to be our true solution, which is here, but you can still see that we've got some error there.
That's pretty significant error.
It is pretty significant error. So how can we do better?
More.
More, do it more. Less subdivisions, more iterations, we'll call it. Okay? So, here we go. X initial is still 0, Y initial is still 0, but now we're going to go in 4 steps. If I go from X of 0, X equals 0 to X equal 4 in 4 steps, then my delta X is 1. I'm changing each time by 1. So, X1 is 1. My initial X is 0. My first X I go to is 1. Y1, differential equation style, is Y previous Y. So Y initial plus dy dx at the previous point, which was 0, 0, times an x change of 1. All right, so the previous y was 0. What's the rate of change at 0, 0? We've done that a lot. 0, so that gives me a new y of 0. I took a horizontal path to the point 1, 0, but now I'm going to recalculate. X2 is 2. Y2 is y1 plus dy dx at the previous point. What was the previous point I just left off at? 1, 0 times another x change of 1. The previous y was 0. What's the derivative now at 1, 0? 2. So that takes me to 0, or 2, 2, right? You agree? I went to the point x2, y2. x3 is 3. y3 is y2 plus dy dx at 2, 2, the previous point, times the delta of 1. We left off at a y2 of 2. The new slope is 2 times the new x, which is 4. So y3 rather is 6. Now I'm going to go to 3, 6. And I'm going to calculate new slope again. X4 is 4. That's the destination I wanted to get to. What happens when x gets to 4? So this is my last iteration. Y4 is y3 plus dy dx at 3, 6 times the delta of 1. That means starting at 6, I'm going to now change by a, 6? And so my last y is 12. Now, you can see then that that does a much better job of following the curve. Although it's still not perfect, it's getting there. And if you kept going, you would minimize this error. This error would get less and less and less and less, and you'd start to get the perfect estimate. Now with the program and the calculator, that's beautiful. For us, we'll usually stick to a few iterations, 2 to 4 iterations max. All right? Okay then. Now, just to summarize the ideas before we get to the formal analytics of it without the graph. Obviously, the more recalculations of slope you use, the better the estimate. That's a big idea of calculus. When else do you say more is better? Rectangles, yeah. The more rectangles or trapezoids, the better the integral of a definite integral estimate. We also used it in Newton's method. Remember when we
had a curve here, and Newton's method said draw a tangent line at any point and see where the tangent line is 0, but don't just stop there, do a new tangent line at that point, and you'll get an even better estimate and better. That repeated iteration also happens in Newton's method. Happens quite a bit actually in numerical approximations. Okay, so this repeated estimation is the heart of Euler's method. Why not just integrate? We could have just integrated dy dx equals 2x and said y equals x squared. Why do all this stuff? Because you can't always integrate. All right? You usually use this method because you can't always integrate. Okay, so Euler's method then is the idea, and I'm trying to cover my bases here on all different possible notations you'll see in college textbooks and the AP test. Given a differential equation, it might be written dy dx, it might be written y prime, a lot of college textbooks write it that way. It might be written f of x, y. Now, first of all, don't worry about there not being a derivative notation. F still represents a derivative that you're being given. Cool? Second, I'm not sure if you've seen that notation before. F of x and y, that's very common, not only in this class, but definitely in Calc 3. You often say that based on whatever x and y are, that might be how high you go there. V depends on, as a function of both x and y. So this is pretty common. My point is this, though. A derivative can depend on x or y or both, just by way of review, because this is an important part of the idea of calculus. This graph, it's a function, yes? Would the differential equation depend on x, y, or both? Let me phrase it this way. If I wanted you to give me the slope at a point, would you need to know x and y, or just x? Just x. If I gave you x, you could tell me the slope, right? Okay. What about this, a non-function? If I asked for the slope at a point, could I just give you x? No. So in that case, the derivative would depend on both x and y. So I guess my point is the derivative could depend on x only, x and y, or y only. Okay, so it could be any of those variations. That's why they're using this notation. It's fun, either way. Euler's method works for all three cases. The point, though, is to get a new y, you use the previous y plus the rate of change at the previous y times an amount of change in x. And you do that in however many iterations they usually will ask you. It's not usually up to you to how many you do. They'll tell you. All right? Let me show you the work I expect to see, although what I just did is pretty much what I want to see. So consider this. dy dx equals 2x minus y. It's a non-separable differential equation. Whatever, autocorrect didn't like non-separable, but I spelled it right, so whatever, I don't care. Estimate y of 4 using an initial of, I'm going to change this to 0, 1. 1, 0 goes from an x of 1 to an x of 4. That means in 2 steps, that means fractions. I didn't want to go down the first example. So we're going to make this a little thing. Okay?
If we use unequal steps.
That's a good question. The answer is yes. You don't do that on the AP test, but in college you do. Especially in college, you're often working without a calculator or a graphing calculator. And in that case, you want to choose values that are clean, that square root nicely or log nicely. So yeah, absolutely. That's a good question.
Could have done 1 to 4, then went from 1 to 2.
Yeah, exactly. Yeah, and so we won't. Maybe I'll put one of those on extra practice, but it's not very common in our life. Okay. So, I'm not going to draw the picture, basically because the slope field I could do it, but it takes time. It's not even necessary. It's nice to learn from, but it's not necessary. Start with x initial. You're going to have an x column in your work and a y column. The x column will be nothing. You're just naming the x's. There's no work to it. The y is where the work. You'll, obviously in your problem set, you won't write x column, right? You understand that? Okay. You laugh, but the pre-algebra kids, when I say, all right, write this, they actually write that. Whatever, it doesn't matter. So, I'm going from in identifying x, after you do this, would you identify, I guess I'll call it step one, identify delta x. I'm going from x equals 0 to x equals 4 in 2 steps. So delta x is 2. I guess a lot like the one we just did, which I didn't. You with me? Okay. All right, good. The y, the x and the y's. First, identify your initial. I know it's given, but it's good form to say the initial x is 0 and the initial y is 1. Given. Cool? All right. The first iteration is to go 1 delta x over, which puts me at 2. y1 then would be y initial plus the rate of change, dy dx. Please communicate to the person at what value you're finding the derivative. The previous value was 0, 1. You'll always use the previous x and y for that rate of change. And then at a delta x of 2. At that point then, you simplify it however fast you can without making an error. I can tell you the most common error is arithmetic errors in trying to do the slope too much or too fast or mentally when you're not up to it. You've got to know yourself, okay? If you make arithmetic errors, then I would here go, all right, here's dy dx at 0, 1. It's 0 minus 1. If you need to show that to get it right, do that. If you can do it mentally, do that. Whatever. 1 plus, or 1 minus 2 is? Negative 1. Are you with me on the first iteration? Okay. x2 then, our final x. We've done this twice at this point. x2 is 4. That's our destination. y2 is y1 plus the derivative at the previous point, which was 2 negative 1 times the delta x of 2. That gives me a value of the previous y was negative 1 plus the rate of change at 2 negative 1 is what? 4 minus negative 1 times 2. I think I did that right. So negative 1 plus 10, so 9. We would estimate y at 4 as being approximately 9. Okay? Questions? All right, try the next one on your own, please. I'm wording it slightly different than the previous one. I just want you to get experience with different ways they're worded, but it's the same thing.
But isn't it negative?
Oh, this is, you're right, this is not a previous y4, is it? Sorry. This should be 1. 13, right?
Yeah.
Lots of places to make errors, right? At least for me.
But it's negative.
Is that negative 455? Okay. Is that a separable or non-separable differential equation? It is separable. It's something you should recognize. What is it?
That is
Oh, you're killing me. Wow, you're only supposed to have memorized 2 differential equations. This is one of them.
Oh, that's really just
It's logistic, yes, it's logistic. Okay, with the carrying capacity of 4. Now, this should look like this, yeah? Okay, this goes to the weakness of not using too many steps. They used the slope here, and they said the slope was up 12, so the first point took them way up here, way above. At that point, the Euler's method said, oh, geez, I'm way too high, so now I need to go lower, but whoa, I mean way too low, so they're obviously coming in wrong. But if you did more steps, it would start to look like this. Yeah, it would start to follow.
Yeah, we were close.
Yeah, that's pretty close. Yeah, it's pretty close. Okay, I'm going to do this as a warm-up in the interest of time. We'll do that as a warm-up tomorrow, so let that go till tomorrow. Let me go over really quick the answers to the fun sheet. Fun sheet. There it is. Okay. These I changed for next year. Okay, so unfortunately, these first 3 were almost all the same. They all compared to the harmonic series, which I changed for next year. That was terrible. They all changed compared to the harmonic series, so they all diverged. Did you give me a full conclusion? Okay. This one, what did you compare to? Okay, does that converge? Actually, was the limit finite between 0 and infinity? Yes, so they behave similarly, and they both converge. Okay. Okay. What test did you use here? E-series, converge or diverge? Which one here? Converge or diverge? What one here? Okay, now you could use comparison here or there, but direct is harder to set up because of the inequality. So when you choose, you should choose the easier one for direct and the harder one for LCT. So this one works well by direct comparison. Converge or diverge? Converge. Limit comparison test, converge or diverge? Converge. Okay, what test there? You can use divergence theorem or nth term test, however you chose to call it. They're the same thing, and it diverges. Does divergence theorem prove divergence?
No.
Yes. Does it prove convergence? No. It does not. Okay. What did you use here? Telescoping. What was the limit of your partial sums? Does that prove convergence? Yes. If there's a finite limit, then obviously it converges. Does that mean the terms converge to 1/2 or the sum itself converges to 1/2? The sum itself. Okay, what did you use here?
Integral.
And what did you say?
Converges because of the integral.
Converges because the integral converges. Truth 12? Diverges by the divergence theorem. The terms don't go to 0. What do you use here? Ratio test. Converge or diverge? Converge. And what do you use here? Root test. Converge or diverge? What is it? Converge, yes. Okay. What's the conclusion of these 2 tests look like?
0 is 0.
0 is less than 1, or whatever the limit is. Whatever the limit is, I guess it could be something besides 0, but less than 1. Okay. All right. That's this. Okay. These. I caught a mistake. Thanks, Lacey. 0.96173, 71.1988, and, there's a lot of uh-oh, 22.1106.
Hey, well, I was really close on this one.
Really close. That's close for nothing.
I know.
Oh, that's right. You're right. You guys verified. Okay, and then the last one we did in class. Do you have questions you want to go over together?
I got one wrong, but I think I know it. Try it and see.
I'll walk around individually if you need help finding an integral error, let you know, or a polar error. Let me know if you have any questions. Okay.